Hi, my name is Kosta. I'm one of the designers working on Bifrost, focusing primarily on the simulation graphs and workflows. Today I'll be showing you how to quickly get up and running with some Bifrost Aero simulations, and then I'll get into some of the details behind the thinking and intentions of the graph layouts and the workflows. With the Bifrost extension from Maya installed and loaded, the quickest way to get started with any Aero simulation or any other type of simulation for that matter is through the Bifrost browser. Today we'll be focusing more on Aero simulations. So under Maya's Windows menu, you'll find something called the Bifrost browser, and in there you'll find several categories of presets or graphs that we've made for you, showcasing some of the most important effects and the most convenient ones already set up for you. The Aero simulations are spread out amongst two categories. The first one is only for smoke and fog type simulations, and the second one also includes the combustion system, so things like fire and explosions. The first one we'll be looking at today is the billowy smoke plume. So this is probably the quintessential rite of passage for any Aero Solver. Being able to make a nice plume of smoke is probably the best place to start. So with the desired effect selected, you have two options. You could either import the effect into your scene, into your current working scene, or you could open the selected example in a new scene. So if you're working in a scene that you want to stay in, then use the import. Otherwise, open it in an example just so you could see it more in context. If you want to see it with some nice lights and with a cool render, then you could open it in the example scene. On a side note, for more details on how to create new graphs and where things are spread out in the Maya menus for Bifrost, please refer to some videos that are on the Learning channel. With that said, we can now go ahead and import the billowy smoke plume effect. So with it selected, I hit the import button. What happens here is that a brand new Bifrost graph is created. You can see that it shows up in Maya's outliner and named appropriately, and also you'll notice that a BIF shape is created. This means that there's something connected to the output of the Bifrost graph, and subsequently the shape is drawn into the Maya viewport. In this case, it's the Aero volume representing the billowy smoke plume. The graph automatically sets up all the nodes required for the simulation and hooks them up for you, along with some backdrops to give you some information. For somebody who is looking at this for the first time, it might seem like a whole bunch of nodes, and it might seem a little bit inaccessible or confusing or scary or any of the above. And so before I get into more details about how to play with the smoke plume effect, I would like to kind of go back a little bit and share with you why the graph is comprised of these specific nodes and why they're hooked up in the way that they are. And to do that, we'll be starting a brand new simulation from scratch. When work first began on the Bifrost simulation systems, starting with Aero, it was very important for us to ensure that simulations were easy to set up and intuitively tweaked, while always maintaining the real physical accuracy and behavior of our solvers as the default for instant beautiful results. Meaning, where most solvers require a lot of manual modifications and operations to approach behaviors matching physical reality, ours begins as physically accurate and requires user input to be artistically directable. I do urge you to check out the videos created by Michael Nielsen and Robert Britson on the underlying numerical methods and physics that drive our solvers. I'll now show you how to begin setting up one of these graphs. With a Bifrost graph or board already created, the first thing I want to do is select a geometry that's going to serve as the source or emitter for your Aero simulation, in this case just a simple sphere. So we'll just want to bring that in by middle dragging it into the board. And now you'll see that a node is created with the name of the sphere, and this purple port here represents the object. So one of the first things that I thought was very important when thinking about how the graphs would look was that we wanted the user to not have to worry about what data they're passing around. Not only would this minimize the amount of wires inside the board, but it would also make them easier to read, and it would also ensure that the user is not always wondering whether or not they need a certain connection or not. So it was very important for me that we have one connection that's passing through the board from the input to the output from each node. Obviously, this is not always the case. We will see situations where you may want to have multiple connections, but overall, the idea is that the user doesn't have to worry about which data they're going to connect from one node to another, because they're always connecting this purple port, which we refer to as the Bifrost object. So having brought in the sphere into the board, we now have a Bifrost representation of the sphere, which is a Bifrost object. With that out of the way, we can now start building up our Bifrost Aero simulation graph. As mentioned earlier, we want the sphere to act as an emitter or source. We prefer to use the word source. And in this case, for an aero simulation, we want the sphere to be a source of air. And so if you do a tab search inside the graph, and you search for source, you'll find source air amongst other sources that you would need for different kinds of simulations, but we're just going to focus on aero today. And so I'll get a source air, and I will connect my sphere to it. As you can see, there's one port that's available to you, and it's called geometry, and so it's ready to receive the geometry. And if we look at the source air node, it's going to have a bunch of properties associated with sourcing air from a geometry. This just means that all of these properties are going to be now part of the object that we mentioned earlier. So when the object came in, this data represented just a mesh sphere, and now this mesh sphere is going into this source air, and so whatever comes out of here is going to have all of these properties initiated. And so once we have connected our sphere to the source air, one might think that you would just connect the source air to the output node and voila, you have an aero simulation, but you actually need to solve for the simulation, and so for that you need a simulate node. So we'll look for simulate. So we have this thing here called Simulate Aero, and you can see this has a bunch of ports, and the one we are looking for is sources. And so here we go, we connect that to the source, and then we take the aero volume and we hook it up to the output. And so this simply just reads, hey, I have a sphere, I would like my sphere to become a source of air, and then I would like to solve the simulation and output it to Maya. So it was very important for our graph to follow the thought process, or the process we would think is most common for a user, which is kind of like a linear task-based workflow where you just are literally telling a story where you're saying, hey, I have my sphere, I am sourcing air from it, I am solving it, and I am outputting it to Maya. And so if I now press play, we'll see that I have some air rising out of my sphere. Now why is this air rising, and why can I see it? Well, the answer to that is because when you create the aero source and plug it into the simulate aero, inside the simulate aero, we're also going to create a kind of environment in which the simulation will take place. And so this environment, amongst other things, contains ambient temperature and the physical force of buoyancy. And so the ambient temperature by default is set to 20, and the buoyancy by default is set to the inverse of gravity, which is minus 9.81 meters per second square. And so what happens is, if we look at the source air, this has a temperature of 580 degrees, and it has a fog density of 2. And so that means that compared to the ambient temperature of 20 degrees, combined with the force of buoyancy of 9.81, the air that's being sourced from this sphere will automatically want to rise. Which is why, once again, if I play back the simulation, the air will rise. Now, I mentioned that the source sets the temperature on the fog, but obviously that's not the only thing that it does. It has a whole bunch of properties here that make it very convenient for you to set up your simulation. So things like when does it start to emit air? Do you want it to stop emitting air at any point? And if so, at which frame would you like to do that? Then there's a whole bunch of stuff here about the resolution. Now, the first thing that needs to happen in order for this mesh sphere to become a source of air is that it needs to be converted into a volume or a level set. And so somebody may or may not be aware of that depending on the type of user, and so we wanted to make sure that that burden is taken away from the artist and that it's handled automatically by the source. This doesn't mean that you cannot do it automatically if you wanted to, but for the sake of this section, I'm just going to explain what the source is doing for you. So Over here, I'll talk about the resolution mode in a bit, but the important properties that we have here are the geodetail size and the fluid detail size. Now, the geodetail size is the detail at which this mesh sphere is going to get converted into a level set. And the fluid detail size is the detail of the fluid that will be emitted from this level set. Now, in some scenarios or in some systems, these two are the same, meaning you don't have separate control over the detail size of your level set and the detail size of the resulting fluid. In our case, you have independent control, meaning that if you had a very, very, very detailed input to your source, but you didn't necessarily want that much detail when you're emitting smoke from it, you can get away with having a coarser detail size for your geometry and then adjust the fluid detail size at the detail that you require. Now, you also have the option between solid or shell modes, meaning that if your geometry is closed like a sphere, then you use the solid mode. This is the most common mode, and that's why it's the default. However, if you wanted to put in a pipe that doesn't have any thickness, or a plain mesh, or anything that has a hole in it, then you would use the shell mode. And finally, if you want to dilate or contract the level set that's resulting from the input geometry, then you could use the geo volume offset. The resolution mode that you see here was designed to allow users to choose whether or not the detail size will automatically adjust internally when the size of the input geometry is changed. The reason this feature was added is to prevent situations where a setup produces so many voxels at the start frame that the machine runs out of memory or Bifrost and Maya hang. For example, if I create a preset out of my current simulation where my input is a sphere of about 2 Maya units in diameter, and I give it to another user who applies the same graph to a geometry that's 100 or 1,000 times bigger. So the input sphere here would be a sphere that's 100 or 1,000 times bigger than the one in my scene right now. Then that would produce an exponentially larger amount of voxels, so much so that their computer might crash or Maya and Bifrost might never recover from the hang. And so this is why we came up with the relative mode, and we changed that so that it's the default. The relative mode, what it does is that it allows the detail size to adjust depending on the size of the incoming geometry, so as to always have this approximately the same total number of voxels for any given specified size here. So for a fluid detail size of 0.05, whether I have a sphere of 2 units in diameter or I have a much bigger one, I could always go back to frame 1 and I will not see any performance degradation due to an increased number of voxels. However, if I were to switch over to absolute mode, then this would not allow the fluid detail size to adjust internally when I grow my sphere, and thus it will produce a much larger amount of voxels and take a much longer time to simulate. Earlier I mentioned how the source error compound takes away the burden of converting to volumes for any user that's not aware that that needs to happen before they can emit from their geometry. However, this doesn't exclude the possibility of somebody customizing their volumes and building them prior to passing them into the source. So if we look up for a node called convert to volume, we could simply connect our geometry in here, and you'll notice that some of the properties that are present here, with the exception of the fluid detail size, are also present on the convert to volume node. So you have the detail size, you have what volume mode, you have the offset, you have the relative or absolute resolution, etc. And then you have some other properties which are specific to creating volumes from geometry, such as do you want to store a level set, do you need a bigger bandwidth of high resolution at the specified level set, so on and so forth. And so if I output the result of this and I return to my viewport, I'm actually gonna disable the arrow just to make this a little bit more obvious. So by default we store the fog density, but if you want to see the level set, you just have to turn that off and turn on the level set. And so now we see the volume that is associated with the sphere geometry. And so when you're creating the volume from the source error, it's essentially doing this for you, you don't get the result drawn out. But if you prefer to do it prior to simulation, then you can simply pass this in and output your aero volume, and then it'll simulate just the same as before. So aside from these two sections that cover the general properties and the resolution properties, we also have the air properties, out of which we've already discussed the temperature and the fog density. These are probably the most fundamental properties that you will want to control when you're first setting up a simulation. And then you also have initial speed. So we already know that due to the environmental ambient temperature of 20 degrees with the internal force of gravity and the temperature that we set will automatically create a rise for the aero volume, we could additionally add some speed to that, so it'll give it a certain push in one direction or another. And here we've separated the magnitude of the push from the direction of the push, which can make this feature a little bit more versatile depending on how you want to adjust it later on. And now for each one of these, for fog, for temperature, and for speed, you can choose the mode at which it will be applied. So there's a whole bunch of modes. These are slightly analogous to the different layering options you have in Photoshop, or you can choose whether it gets added or it gets subtracted or it's set or min-max, whatever. So this allows you to input fog or temperature or initial speed at each time step according to a different mode. And so the best way to really understand the effect each one of these modes will have is to just play around with them and see what works best for you. And then the other two parameters we have here, inherent velocity and trail smoothness. So inherent velocity, what this does is that if your incoming geometry is animated, you can control how much of that velocity will be passed on to the aero simulation. So for example, if you have something moving really quickly that comes to an abrupt stop, then through the force of inertia, the emitted volume of smoke will continue moving after the emitter has stopped moving, and eventually the forces of buoyancy or whatever will take over. Conversely, if you want to produce the effect of thrust, then you can set a negative inherent velocity. So what this says is that, well, I see that your object is moving in this direction, so I'm going to give the aero the opposing equivalent but negative force of thrust. And then finally, once again, for moving emitters or moving sources, the trail smoothness will determine whether or not your trail is smooth. So sometimes, depending on the size of your emitter or the speed at which it's moving, you may get a little bit of a stepped emission. And so rather than have a smooth trail, you can have a choppy trail. And so increasing this number will make it smoother. However, this will also result in a little bit slower simulation times, longer simulation times. Up until this point, I've been referring to this environment, which is created when you simulate that, amongst other things, will set the force of gravity and the ambient temperature and so on and so forth. And I've been saying how this happens automatically inside the solver. Well, one thing we were very certain about when we were thinking about the workflows and the graph layout and all that stuff is that we didn't want users to have to dive inside compounds to find things and to set properties. And so if you look on the Simulate Aero node here, there's a port called Settings, and if we do a search for Settings, Settings, then we'll see something called Aero Solver Settings. And if we get that and look at its properties, basically everything I've been talking about until this point concerning the environment, you'll find on this node amongst other things. So here we see the ambient temperature, which is set to 20. We see the force of buoyancy, which is enabled and set to minus 9.81. And there's a whole bunch of other things that I'm going to speak about as well. And so even without this node present, there are some defaults set inside the solver so that even if you don't know that you need this node, your simulation will still work. But once you want to start tweaking the properties of the solver, then you just need to connect this to the settings port. So before I get into all the details about all the different properties that exist on the Aero Solver settings, I just want to backtrack a little bit for a couple of minutes and show you how you would proceed with having various geometries input as sources for air and various sources, because it's all going to tie in together when I start talking about the solver settings. So let's say you're in a scenario where you have one emitter or one source of aero, and suddenly you decide you actually want two, but you want him to emit the exact same volume of aero with the exact same properties. So this is my first sphere, and so basically I would just grab my second sphere, bring it into the board, and then just simply connect that here. Now this port is called a fan-in port, and it can be expanded, but if it's collapsed, then you could just bring everything onto the same port and it gets appended. And if you want to see all the geometries hooked up to their individual ports, you just expand this here. So now we'll have both of these spheres emitting smoke according to the properties that are set on this source air. Now you may find yourself in a scenario where you want yet another source. So in this case it would be the torus, and I'll just move it to the side. However, you might say that you don't want the torus to emit with the same values for these properties. Maybe you want a different fog density, or you want a different temperature. You could even have a different fluid detail size, which is really one of the strengths of Bifrost, is being able to have various resolutions for any given simulation without having to do two different simulations. And so we could have a look at that as well. So what we'll do here is we'll bring the torus in, and then we'll create a new source. And you can see that this source just has the same defaults that exist on the first one here. And so I'll just connect my torus here. And then on the source, maybe I'll say, you know what, this torus is going to be somewhere in the background or whatever, so I don't need to have the same resolution. So maybe I'll give it a resolution that's a little bit lower. So by increasing the detail size, you get lower resolution. Maybe I want it to start at a different frame, so rather than it starting at frame 1, maybe I want it to start at frame 5. Maybe I want it to have much lower density, and maybe I want it to have a much higher temperature, 1000, or maybe I even wanted to have some initial speed in one direction, so I'll put the magnitude of the initial speed to 1 and the vector in the x direction. Actually, I'll make this a little bit bigger just so that it's more obvious, so I'll put that to 10. Just like I can add multiple geometries to any given source, I could add any number of sources to any given solver. And so the simulate aero here, where I have my sources port, is also a fan-in port just like the source air, and so I could just add my second source here. This is gonna refresh my simulation, and so now if I go and expand this, I could see that I have two sources of air that are working in the same simulation. And if we play back this simulation now, first we'll notice that there's a slight delay between the emission of the two spheres on the torus, because we had set the start frame of the torus to 5. We'll also notice that the resolution of the smoke emitted by the torus is slightly more chunky than the one being emitted by the spheres, and the fog density is also slightly lower. We also gave this a little push in the x direction, and so just to have a better look at that, it's just going to turn the camera a little bit, and so you could clearly see that the resolution of this plume of smoke is lower than this one here, but this is not preventing them from interacting. You can see that this one's pushing on this one, and that eventually they will start to mix. Now what happens when two plumes of different resolutions mix is that the one that has the highest resolution will win. And so when these two plumes start to interact, eventually the areas that are getting mixed will all convert to the smaller detail size, which is being contributed by the middle sphere here. Okay, so now that we've covered hooking up multiple geometries to one source and hooking up multiple sources to one Aero simulation, we can go back and talk a little bit more about the Aero Solver settings. And just do keep in mind that this could go on ad infinitum, obviously with certain performance degradations, so please do keep that in mind. First, I'll press the L button to lay out the graph neat and tidy, and you could also always collapse these ports to make it even cleaner. So let's have a look at the Aero Solver settings. So the first section here on top is just some very general, useful controls, such as is the solver enabled or not. So if I want to just disable my simulation without breaking any connections, I'll just turn that off. And then we also have something called the master start frame. Now, earlier we saw that this source error is set to start emitting at frame 1, and this source error is set to start emitting at frame 5. And just imagine I had a few more sources, all with different start frames. Well, maybe for debugging reasons or for some reason, I would want to just have them all start emitting at the same time without having to go in and individually change the start frames and then change them back. So maybe I could, so in that case, I'll tell the solver, okay, well, use this master start frame. I actually want all of the sources in this simulation to start at frame 5, and so I could just set it to frame 5. And then if we have a look at that, we'll see that they all start at frame 5. So that's something that could be very useful in certain situations. Store mass density, I won't get into too much detail about that right now, but it's a channel that you may want to use for rendering, and so it's an optional channel. That way it's not always being carried through the simulation, which, I mean, the more channels you have, the more properties you carry through as data in the simulation, the slower things will get. And so this is one that doesn't really have any effect on the actual simulation, but can be used at render time to produce various effects, and hopefully we'll have a video about that sometime in the future. The next thing we'll look at is this other section called the Aero Solver globals. Now, why are they called globals? And this is another reason why I wanted to introduce the concept of having two sources, because as we saw, each source could have its own air properties, could have its own resolution, could have its own start frame, so on and so forth, and these are all associated with the geometries that are connected to them. However, anything that is changed here is applied globally. It's indiscriminate of the sources. It's just going to affect the entire simulation. Doesn't matter how many sources you have or what's going on. Changing anything on the Aero Solver globals will affect everybody. So these are kind of like local properties that are associated to each source and each geometry, and these are global properties that are just applied everywhere simultaneously. So things like the ambient temperature, every source is going to behave according to the ambient temperature that's set here. Style, I'll just get back to that in 2 seconds. Simulation speed, how fast do you want the simulation to go? Obviously things like temperature and buoyancy and initial speed, whatever influence fields you may have, which we're going to look at later, will affect the speed of the simulation, but you might want to have, you might want to control that, you might want to override the natural speed of any given simulation, and so you might want to make it faster or slower or whatever. And then here is the buoyancy, as we had talked about earlier. Is buoyancy enabled, and what is its value? Velocity smoothness, this is something that you may want to use to create silkier looking smoke, or in some scenarios if you start to encounter areas of maybe jagged movement or some artifacts, which is not very common, but it may happen. So in that case you could smooth out the velocities, and in doing so, it'll just create a much smoother looking simulation. Now, obviously, if you want something that's super highly detailed, like pyroclastic smoke or something like that, you'll want to leave this at 0. The kill voxel fog threshold is essentially a way of saving on performance by not tracking any voxels that have a fog density below this value. So this is just telling the solver, if you encounter a voxel that has a fog density value less than this, please kill it, don't track it anymore. Now, obviously, the fog density is set here. So, this source has fog density of 2, and this source has a fog density of 1. And so both of these numbers are much higher than 0.01. But as the simulation goes, depending on what happens, if any voxel is to fall below this threshold, then it will be killed. Now, if you want to have some very, very thin smoke, maybe some mist or some cigarette smoke or anything that looks like a very thin veil of smoke, you may want to decrease this value, because you may start to see voxels disappearing in an unnatural way, in which case you'll probably want to lower the threshold here. Again, this is going to imply that you're going to actually track a lot more voxels, and so you will have a little bit of a performance hit on that, but used to your discretion. And finally, the scene units in meters. This is huge. This is something that people have been struggling with even from the first incarnation of Bifrost, which was the Bifrost Liquids that came out with Maya 2016.5. Basically, it's having control over the scale of the simulation. Now, there is a learning video created by Matthew Chan that you could find on the Bifrost area, which covers the scene units in great detail. So I'm not going to get into it very extensively right now. The only thing I'll say is that Bifrost treats one Maya unit as 1 meter. And so in this scenario, and I think I maybe touched on this earlier, my sphere is about 6 meters in diameter. So this is a rather big emitter. And so the smoke is going to move accordingly. Generally, when smoke is emitted from a much bigger geometry, it's going to move a lot slower, similar to water. If you look at a giant waterfall, it kind of looks like the water is falling in slow motion, whereas if you're spilling water out of a glass, it's very fast. Similarly, if you want to have a really small emitter, like maybe a cigarette lighter or cigarette smoke, then you shouldn't use an emitter that's 6 meters in diameter. Now, there are situations where you won't want to actually scale down your geometry. In that case, you'll just go in Bifrost on the solver settings and tell it, you know what, don't look at a Maya scene unit as 1 meter, look at it as 1 centimeter. So I would change this to 0.01. Now again, for more details on this, please refer to the video that exists on this topic on the Learning channel. So now I'll go back and talk a little bit about the style property that exists on the Aero Solver globals. Internally, what this does is it changes the interpolation of the transport between linear modes and cubic modes. Now, if you want some more details about what that means numerically and mathematically, you could refer to the deep learning videos from Robert Bridson. But what I'm going to talk about is basically what kind of look you get when you change from one to the other. And we've named them according to, what kind of style it gives the movement of the smoke when you change between the modes. So smooth is obviously just that. It's going to be a smoother type looking smoke, not a type of smoke that's very, very billowy or highly detailed, more like a cigarette smoke or, a more relaxed kind of look. Fluffy, the other three are basically fluffy, busy, and wispy, are the cubic interpolation modes, and these give more of a billowy look. So things like, like a smoking chimney in the winter, or a fluffy cloud, or any of that. But I guess the best way for you to understand what the difference is by seeing an example. And so here, I've done a play blast of, on the left you have the smooth or the linear interpolation mode, and on the right you have the fluffy or the first cubic interpolation mode. So you see that there is way more details, way more little puffs coming out, whereas this one is smoother. And so if we actually play this, you could see the speed of the rise of the plume is still the same, but the dynamic is quite different. And so once again, on the left we have smooth, and on the right we have fluffy. And now if I were to change it again to another one of the cubic modes, so either busy or wispy, oops, sorry about that. So the busy mode would look similar to this one, but with even more details and a more chaotic kind of movement, a much more billowy. And the wispy one would be just a little bit more tame. So the wispy would land somewhere in between these two. It's not quite smooth, it's not fully fluffy, so we just called it wispy. And once again, I'll emphasize that the style is actually a solver global, so once you change from one mode to the other, it's going to affect every source you have. You can't set one source to fluffy and have another source set to smooth. Once again, this is a global property, so it's going to affect the entire simulation. The next section here, it has to do with accuracy and time stepping, and so this is going to determine how many iterations the solver will do per time step, and this will increase the accuracy of the overall solve. Now, we've found that by default, having a rather large step size, a rather large time step size and a low number of sub-steps in general produces some pretty accurate results. So by default, this is a good place to start. However, if you have a mass of smoke that needs to move very, very fast, and I'm not talking about the geometry moving fast, I'm talking about the the volume of smoke itself moving fast, either because you have some very large initial speeds or some very, very, very high temperatures, or in the case when we will look at combustion, some rapidly expanding volumes, then you may want to increase the max number of steps or decrease the time step size to get a more accurate solve. So we'll probably talk about that more a little bit later. And finally, diffusion handling is there because there have been situations where you might lose detail at times when you don't want to. And so we have a couple of ways to fix that, and that will also probably be covered at a later time. So the next thing we'll want to look at now is setting up collisions. So just for the sake of simplicity, I'm going to remove the extra geometry and extra source. And so if we look once again to our simulate aero compound, we'll notice that there's a port called colliders. And so we'll search for collider and we'll find the collider here. And we'll set up a collision geometry in the viewport. Let me just make sure I've kept the right geometry. So P-sphere 1, which is here, perfect. And so I'll create a cube and I will make it a little bit bigger, place it around here, and then I will bring the cube into the board, and then I'll hook it up to that collider node. Now, the cube, just like any other geometry associated with an aero simulation, will have to be voxelized, turned into a level set. And so if we look on the collider node, we have some properties for that, but we also have a lot of other properties. Why is that? So as mentioned earlier, there's many simulation systems in Bifrost. So right now we have Aero, there's particle system, and there's also an MPM driven granular system for sand, snow, and some other cool stuff like cloth, so on and so forth. And so this collider actually works for each simulation system. We didn't want you to have to look up a different collider node depending which simulation system you're in. The only catch there is that each system uses a slightly different method for collision. And so up here, you have a general section and the method is set to automatic. So once I connect this here, the collider node will understand that it's connected to an aero simulation and it'll use volumetric collisions. And so down here we have some properties that are unique to volumetric collisions, such as the resolution mode we already talked about earlier, and whether or not your geometry is solid or a shell. Now things like detail size, whether you want to create an offset of your geometry, the inherent velocity are common regardless of which collision method or which simulation system you're in. And then if you're doing particle simulations or MPM simulations, then it's actually going to use the mesh collision method, which has some of its own properties down here. But for now, we only have to worry about the first three sections here. So just like any other node, the collider node has a start frame, it has an end frame if you want to use it. Again, it has a detail size, so on and so forth. And just to repeat something from earlier, if I use the master start frame here, it's also going to affect the collider. So I'm actually going to turn this off now. And so now if I go back and look at my simulation, let me just go back to frame 1, press play. We'll see that the smoke rising from the sphere will collide with the cube. Now you'll see that there's a little bit of a space in between the collider and the smoke. Why is that? Well, it's because the resolution of the level set is actually quite high. So if I wanted the collisions to get more and more accurate, I would have to voxelize the cube with smaller and smaller voxel size. So I would just decrease this. And now if we step back and take a look at the graph and we think of what I was saying at the beginning of this video, where we wanted to have a task-based workflow and to work quote-unquote at the speed of thought, we start to see a picture that emerges where you have this thing here. It's kind of like a machine that's going to do the work for you. It's going to solve the equation. It's going to simulate the error for you. And basically you want to give it instructions. So you're saying, okay, well, I have a sphere. I'm going to initiate some error properties and some functionality on it, and I'm going to pass that information to the solver. Similarly, you'll say, okay, well, I also have another geometry, but I want this one to be a collider. So you're telling the solver, hey, here's the information you need for the collisions that I want. And then you have your solver settings just to control the globals and all the other stuff we spoke about earlier. And so from this picture, we get what we refer to as the template. So this is probably the minimum nodes required for any aero simulation. And so if you do a tab search for basic, you'll get something called a basic aero graph. And now this is packaged up in a compound, so what you would want to do is explode it. And sometimes there's a little bit of an issue with the layout, so I'll just press L to lay that out. And if you see here, it's an exact mirror of everything that I've built up since the beginning of this video. So one source, one collider, one settings, one simulate node, and this is the minimum requirement for any aero simulation. And now from this template, we built all of the examples that you would find in the Bifrost browser. So now, having seen this video and having listened to me share the thought and process that went behind the construction of this template, once you start looking at these graphs, you'll have a better understanding of why things are laid out the way they are and why they're connected in the way that they are. Obviously, those graphs are a little bit more complex. There's some more nodes that come into play, things like influence fields and things like source variations, which we will look at as we start looking at those examples in the following video. Now, on an end note, I also want to emphasize that if you ever want to start using the other simulation systems, such as the particle system or the NPM system, they all have a very, very similar template. So this concept of sourcing, of colliding, and of solver settings all connected to a simulation system is consistent throughout all the Bifrost simulation systems. So once you've learned to understand one type of graph, you want to start experimenting with other simulation systems, the graph that you will encounter will essentially be the same, obviously with certain differences, but overall you will not be starting all over from scratch. You'll already have a basic understanding of how the graphs are laid out for simulation. So stay tuned for another video in which we will look at the examples in more detail and see how those examples were built, starting from this basic aero graph layout.